So welcome to our keynote and panel discussion, and this is a more technical discussion. And we have the title, which is, and I have to read that, the role of FDOs in the next revolution in computing and data management. And I said, wow. If I had a box with question marks, I had to put it out and to put my question marks in here. So, but to get some insights in that, we have Bob. We have George.
George.
Guten Morgen.
Oh. Shoot that man.
Excuse me. We have George Strawn. And George is director for the National Academies, Board on Research Data and Information, director of the Computational Center at ISU, Director of the National Coordination Office, co-chair of the Networking and IT Research and Development Committee of the National Science and Technology Councils. But we didn't invite him because of his CV. So we invited him because he is visionary and he has far-reaching ideas on the future of the internet and global information infrastructure, and also plans how to shape in the fair digital objects. So we are looking forward to your presentation about one computer, one data set. Thank you very much.
Thank you, Rainer. Good afternoon, ladies and gentlemen. I'm very happy to be here. Rainer, thank you for that kind introduction. I'd like to thank the organizers for inviting me. Oh, wait. I'm one of the organizers, so I'd like to thank the other organizers for inviting me. You'll note that I'm sitting. For the last 2 years, I've been giving talks sitting, but on Zoom, nobody knows you're sitting. So it's a little bit like the old joke on the internet, nobody knows you're a dog. So I have this annoying condition, which is a lack of balance. The only serious ramifications of that is if I have a glass of beer or a glass of wine, I fall over. So that's the serious ramification. Everything else is okay, though. So one computer, one data set, speaking metaphorically. I'll talk about motivations, and then the past, the present, and the future. The past is many computers, many data sets. The present is one computer, many data sets. And the future that we are looking toward is one computer, one data steps. I'll end up with a few remarks about what I think might be next steps. Motivations, well, open science. And open science, the original open science, as you know, consisted of articles published via the printing press, which was already 200 years old by the time the Royal Academy suggested publishing articles. But that's number 100 years ago, and now we have a new open science, a vision of a new open science, which is sharing all of the science outputs. And of course, it's via network computers, not via the public, the venerable printing press. But all outputs include articles, data, software, workflows, etc., because all of these can be encoded as digital objects. Why do we do this? Well, sharing all science outputs, we believe, will not only produce better science, it'll produce better science faster. So I think this is the next step, the next scientific revolution. I might go so far as to say this new science revolution will be as revolutionary as the original open science revolution was. We shall see. Fair digital objects is a technology designed to simplify the sharing of all science outputs. Now here I say a technology. I understand that we have at least 2 communities represented here, which is just fine, and I endorse both of them. Number one is looking at one or more particular technologies to implement the concept of fair digital objects, and the other is a broader understanding that many other approaches to fair digital objects might very well emerge over the next period of time. if we use small letters, FDO, as a general concept, I think the idea of the emergence of this new generation of open science has to happen and will happen because it's the right idea. Do we know exactly how it's going to happen or when it's going to happen? No, that's up to you all. You will produce it, and we may bank on one technology, and it may turn out to not be as good as a second technology. Don't forget, there was a time when token ring was guaranteed to replace Ethernet. That's for you oldies to remember. That never happened. A lot of the technologies we think are going to happen will be superseded by new ideas as creative people continue to think, and that's fine. Just remember that we always overvalue our technologies in the short run and undervalue them in the long run. We think we know more than we know today, but when the time comes, the revolution will be of greater magnitude than we can probably realize today. Now, one last introductory word, and then I'll get on with my work. You may think I'm old enough to have invented the digital computer. I did not, but I knew the man who did. And I have known Bob Kahn and Vint Cerf for about 30 years. And now I know Baron Mons and Peter Wittenberg and their colleagues. So you see, I have 3 generations of connections from the computer, from the network, and now from the digital objects. So I've got plenty of stories that I can tell as time goes on. There are, of course, plenty of motivations for what I had called open science beyond science. Fair digital objects has originated in the science community, just like the internet did. And fair digital objects, some of us say, will become equally important for persons in business and government, just as the internet has. I mean, the web, Google, Amazon, etc., are certainly no longer restricted to the science community. Business and government certainly may not open all of their digital objects to the world, just as science hopefully will do, but within their more limited domains, they will certainly share more data and software as the sharing is easier. Easy is one of the words we really need, right? The technology has to be advanced and has to be easy to use. So that's something to keep in mind. Baron always points out, and I think it's true, that fair is not identical to open. He uses the phrase, as open as possible, as restricted as necessary. And I think that's a good way to look at it. All right, let's look back. I'll talk about the first phase of history from 1936 to 1995. 36 was a theoretical development. Those of you who've studied computer science will know that Alan Turing defined computability, which hadn't been defined before that time, and proved that software machines, also called abstract machines or virtual machines, can be built on top of hardware machines to simulate anything that a hardware machine could do. I would say computer science per se has lived on that observation ever since that time. We develop new hierarchies of software machines on top of basic hardware machines to develop advanced capabilities. I remember some years ago the U.S. Patent Office recognized that a computer with a certain software loaded on it was a different machine for patenting purposes than just a raw computer. But I want to pay respect to the hardware giants. We stand on their shoulders. If you look from computing, of course, tubes in the 40s, transistors in the 50s, chips of transistors starting in the 60s and 70s. Look at the Moore's Law, a wonderful development. We could put 1,000 transistors on a chip in 1970. We could 1 million on a chip in 1990. We could have put 1 billion on a chip in 2010. Looks to me like we're on our way to having 1 trillion transistors on a chip by 2030. Some special purpose chips have already been designed, for example, with 30 trillion transistors on. And of course, we're just playing around, right? Because somewhere down the road, quantum computers will become real and will revolutionize again what our prospects of being able to do, which we now probably can't truly understand. Let's move on quickly to the present. One computer, many data sets. Now, I've marked this from the commercialization of the internet in 1995, and I optimistically say later this decade. Now, I was with Carole Lubin yesterday of the EOSC, and he's a very realistic guy, and he said he's hoping that the goals of the EOSC will be realized by 2040. Well, that won't happen unless we start now, so don't sit on your hands waiting for 2040. But we're talking about grand projects that take decades to develop, not that take years or months to develop. So remember, we're talking about a marathon, not a sprint, as we continue this development. The commercial internet had an advantage that so far we haven't really had in the emergence of data, in the sense that there were 30 years of sustained governmental funding, in this case by the United States, 20 years of research by DARPA, which produced TCP, and then NSF picked it up in 1985, creating the first infrastructure based on the DARPA research protocols called the NSFNet, which had an original goal of connecting 100 research universities in the U.S. to 5 supercomputing centers. Before we retired the NSF in 1995, we had connected 2,000 universities and colleges. When I went to NSF in 1991, there were a few hundred universities already on the internet. But I thought I would look and see who all was connected to the internet. We had regional networks, and so nobody was connected directly to the NSFNet backbone. They were measures of regional networks around the country. I counted up, and even in 1991, there were an equal number of private sector companies on the internet watching it develop, along with universities and colleges. So in my mind, the transition really had begun by 1991, although 1995 is when we now say it. An old computer company called Sun Microsystems had a slogan way back in the previous century: the network is the computer. All right, that's where I get the one computer, many data sets. Of course, for us geeks, we tended to say the internet is the backplane of a multiprocessing computer, but the thing was the same. You all know, and I'm just simply repeating for the sake of emphasis, that every computer on the internet is given a globally unique identifier called its IP address, and the TCP and IP protocols control the flow of packets between communicating computers. Again, we stand on the shoulders of hardware giants. The fiber optics and laser light is probably as much of a giant as chip technology, although it doesn't get quite as much press as Moore's Law does. But when fiber optics emerged in the 70s, the maximum speed was 45 megabits per second. In this decade, this century now, when we bury a bundle of fibers, it's usually 100 fibers in the bundle, 100 independent information channels on each fiber, and maybe 100 gigabits per channel. So one buried group of fiber optics is perhaps a petabyte of petabit of data, which is keeping pace, if you will, with the number of chips, number of transistors on a chip. Well, even before the commercialization of the internet in the, let's say, roughly 1990 timeframe, this thing emerged called the web. We now know the World Wide Web. I would say this is the beginning of the one data set era that I'm looking forward to in the future. The HTTP protocol and the hypertext markup language built an abstract web machine on top of the internet, which, as you know, and as well as I, there are now billions of web pages interlinked together. And thanks to Google and other search engines, those pages are findable. I can't tell you how many times a day I Google something, and I bet you do too. But for human readers, it's fair to say that these pages are also accessible, interoperable, and reusable. They're accessible because most of the pages on the internet can be accessed free of charge. They're interoperable because we provide the semantics, right? It's human language that we provide, and assuming you're looking at a part of the internet, which is the human language that you understand, you provide the internet. You want to look at another web page in the same language, they interoperate for you perfectly well because of your human capabilities. And those that are accessible are reusable. I steal paragraphs off web pages to incorporate into articles that I'm writing on a regular basis, with attribution, of course. And I would say that FDOs seek to do for computer readers what the web does for human readers, and to do it with all data sets, not with just HTML data sets. So there's our goal. Computers are our new readers. All data is our new domain. And what can we do for computers that we've already done for humans in the limited but very important aspect of the web? Well, the web, of course, probably can be looked at in this way. If I'm on computer one and I'm talking to my browser and I click on a link and that enacts the HTTP protocol, which goes to TCP, which puts me out on my network, which via routers and the IP protocol gets me through any number of links, eventually to the network containing the web page that I'm looking for. That communicates with TCP/IP, that communicates with the HTTP there, which finds the website and an HTML data set, returns it to me. My browser knows how to paste it. Reason I just mentioned this is because I think this is a very similar diagram to what we are attempting to do right now in a much broader context. And I certainly don't need to take the time to tell you all this. This is just what Google does for us, right? The fact that Google has organized wonderful, huge data sets that connect the words in web pages to a user who specifies some keywords in a search, and in lickety-split, in sub-second time frame, you'll have a million pages that contain those words. And of course, the reason that made Google the leader originally in this was because it figured out how to put web pages that had the greatest chance of being useful to you up at the top of that list of a million. And they did it by using concepts such as references or hubs and authorities. A hub is a page that has pointed to by many people, and an authority is one that is pointed at by many people, many pages. Of course, these days, some people may say the ones at the top of the list are the most profitable ones rather than the most relevant ones. But we have to mix in a little capitalism with this business somehow, don't we? All right, let's look now to the future, which is what we're here to talk about, which I metaphorically like to describe as one computer, one data set, either from the late 20s or the late 30s or somewhere. And as I say, if you don't like poetry, just think about interoperable computers and interoperable data sets to oversimplify. Again, we have hardware giants to stand on. Disk storage has a more distinguished and longer history than either chips or fiber optics. We still don't like disks because it's electromechanical, and we'd like to get rid of the mechanical part, but we can't do it. It remains too good a technology. I'll say a little about that on the next page. Data systems, just to look at some of the data systems, especially the ones that I think may be relevant to the one data set as we go forward. Fair number of slides specifically titled Fair Digital Objects, which is an abstract machine extension of the internet if you look at it. I think Bob Kahn likes to talk about the digital object architecture as an extension of the internet, and I can see how he would be willing to put it that way. Then I'll put a final page on data science, which is this wonderful new emerging discipline that we've decided isn't quite the same as computer science. In fact, the statisticians claim as much relevance there as the computer scientists do, so at most universities it's an interdisciplinary major, which is attracting a large number of students, of course, because of its relevance in industry especially. Disk storage, as I just said, a longer hardware evolution. The first disk storage you could buy was in 1956 on the IBM Ramac 305. They were pleased to offer you 5 megabits of storage along with that relatively small computer. Well, by the mid-'80s, you could get a 5 gigabit disk drive. It's still pretty expensive, but certainly that's a lot bigger than 5 megabytes. Today, 1 to 5 terabytes on a small disk that weighs about a pound and costs about $100, right? So that's another hardware giant, another thing that's as important as Moore's law when we look at the hardware that supports our business. And of course, with a 5 terabyte disk, you ain't seen nothing yet. In the laboratory, there are synthetic DNA systems storing data. Well, if you want to store an exabyte of data with today's 1 pound terabyte drives, that's 1 million terabytes, so it costs you 1 million pounds. And of course, Google and Amazon and other places actually do that. But an exabyte of synthetic DNA storage weighs a few grams. So as Richard Feynman said decades ago, it's still true, there is still plenty of room at the bottom. And since we can already store more data than we can effectively process, what's it going to be like when we are managing DNA, synthetic DNA storage? We better keep working on these data processing activities because we ain't seen nothing yet in terms of big data. So the storage and retrieval of information, which is the focus of what we are doing here, we have for many decades had abstract disk resident data and abstract memory resident data. We've not necessarily used the word abstract, but of course they are software systems built on top of raw hardware. Our disk resident systems have been called files for many decades. Starting in the 80s, we developed a more higher level way of storing things called relational database management systems, with a very clever SQL query language. And now recently, where files have grown so big that relational doesn't always do the job anymore, and so some people talk about no SQL database types. That doesn't mean we don't like SQL anymore. It means not only SQL. We have the big table that is working behind the scenes for us with Google and other types of extraordinarily recently developed and important data technologies. About the same time that relational technology was being developed by Ted Codd in the 80s, the concept of abstract data types was originated. Well, it was actually originated in the 70s in Norway, I believe, in a programming language, and it was called information hiding at that point. And then by the mid 70s, it was becoming clear that this was an important way to think about data. So an abstract data type bundles together a data object along with the means to access the data. Subroutines are called methods, they're called various things, but if you deny yourself access to the syntactic data structure itself and only access and modify your data by these subroutines, that's an abstract data type. And of course, one thing it does is allow multiple implementations. Everyone knows that the best way to implement a data set is based on the operations you intend to apply to it. And so if you have a data set that has a different set of frequent operations in different environments, you implement the data differently to obtain efficiency in the various environments. So I was always attracted to the study of abstract data types at that time, especially since my original education had been in mathematics and in algebra, and it looked to me like abstract data type was a concrete realization of a multi-sorted algebra. But I'll save that lecture for another time. So just as I think that I've already said the last two bullets, the syntactic structure is hidden and multiple implementations are available. Now, it's my view that the abstract data type already plays a prominent role in some of the implementations of fair digital objects. Not necessarily all, but we shall see. Is that a fire alarm? No, let's keep going. Well, let's now focus a few comments on the central topic of the day. Of course, I've just commented on more than one implementation. Well, no, here I mean a different thing. If we write FDO with small letters, not big letters, we can talk about things that based off what Bob Kahn told us yesterday about his digital object architecture and developments in that line that have been pursued by RDA and other investigators. The semantic web, or linked open data, as I guess it's now called, is another candidate. In fact, in my mind, I could imagine that a hybrid between linked open data technology giving us the format for the metadata and the Bob Kahn architecture of digital objects for the quote raw data itself is something that might emerge. And like I said, I'm perfectly happy with the fact that if somebody comes up with a better idea in the next few years, I'll jump on that horse as quickly as the next person, because I know how creative this community can be. And well, let's look at the few pages I have there. I think I've just said the Go Fair activities led by Baron called for the creation of implementation networks, INs, to implement fair data principles. And I think there's still on the order of a dozen implementation networks that are still working to do so. I consider the Kahn activity one of those implementation networks that is going along on with FDO with capital letters, because it has chosen some technologies. So the solution space is still being explored, and that's good. And how many will we end up? Will we end up with one or more winner at some point in the future? Well, if the past is any indication, we'll ultimately end up with one. I mean, we don't still have token ring plus Ethernet, Ethernet 1 over token ring. We still don't have DECnet and OSI and Internet. Internet 1 for various reasons, and DECnet and OSI networks are relevance of the past, let's say. And so it's, especially since interoperability is important, I think we'll end up with a very limited number, perhaps one solution in 10 or 20 years. But that shouldn't inhibit continuing to explore the solution space in any way that your creativity suggests. Is there anybody in the room that hasn't heard the acronym FAIR? I don't think so. I was fortunate that Barron invited me to the workshop where that acronym was formed. And I'm sure he would agree with me that the only thing new about FAIR data was the acronym. Right? People have been working on accessibility, interoperability, et cetera, for decades. And if we don't acknowledge that, we risk stepping on the toes of giants rather than on their shoulders, because we're taking advantage of all the good work that has gone before. But a really good acronym is really helpful, isn't it? What did you say, 8,000 citations already to the paper? All right, we've called public attention, our public, not the wider public, attention to the concept. Of course, this has the danger of becoming either a religion, a cult, or just a buzzword. Any profit-making corporation will tell you that they've had FAIR data right from the beginning, so just sign up with them and you'll be in business. But that's all right. Like I said, we tend to overestimate the importance of our technologies in the short term. It will be more important than we can realize. Always notice that it is a overloaded acronym, as many of our acronyms like to be. Fully AI ready is another FAIR, right? That is, FAIR data is ready, or at least readier for deep learning algorithm training. We know that it takes a lot of effort to get the data ready to put into a training algorithm to give us a machine learning algorithm. And it's, in the US at least, one of the things that where AI has become an important buzzword in terms of federal government support. We say, you need the data, so include data along with AI as you're looking for the additional funding programs in the federal government. And I think that's starting to happen. Objects and PIDs, well, this is one way to show the correspondence, let's say, to webs and web pages. Permanent global identifier, PID, global and permanent, that points to, and in the BobCon implementation, it points to a persistent identifier record of an FDO. There's a level of indirection between the FDO itself and the address. Levels of indirection is a long used and very successful computer science techniques to increase the generality and the applicability of a subject. In the old days, we had to worry about too many levels of indirection because of the processing time that would happen. With nano speed computers, you don't have to worry about that nearly as much as we did with microspeed computers. The FDO itself, just like a web page, is a bit string. But it's got to be more than a bit string. But there are two protocols. I guess we just had the one protocol in terms of the web, the HTTP. Here we have two identified protocols. The handle, or the one that resolves an identifier, and DOIP, the Digital Object Interface Protocol. Of course, as I said before, since we don't know what the FAIR digital object is, since we want to make it self-identifying, and it's not being passed to an application that understands what it's supposed to do. That's what the web does, right? And that's what email applications, most of the internet-based applications pass a bit string to an application that knows how to interpret the bit string. Here we have the bit string. It has to contain enough information that we can interpret it by anybody can interpret it. Well, all right, that means metadata for semantics. It means metadata for security, for access control, for provenance. This is all an area of very active research, I think. One good thing to point out is that for pre-existing data sets, an FDO can point to the existing data set with this overlay on top of the metadata, and you therefore, in the future, at least initially, we won't have to change every existing data set we have, change it out and change it into a FDO format, because this cap that can be put on existing data sets allows us to proceed. And the internet did the same thing, right? The internet didn't replace networks. The internet was a software network that interconnected hardware networks. So you've got Wi-Fi here, you've got Ethernet here, they're connected by a router, and sitting on top at the software level is the internet, which because of the routers and the internet protocol is able to wind its way to the proper destination. So FDO is a more abstract machine than we've had before. Computer science advances by introducing new higher levels of abstract machines. Perhaps you've seen this picture in some of the other talks here, where the bit string is sort of the core, and a PID is pointing at it, and various metadata, scientific provenance, rights, usage records, etc. Operations, that's a special term, which I'll look at on the next page. And this gets back to the question about abstract data types. Should an FDO be accessed only through operations that are part of the metadata associated with it, as with abstract data types? Or should the bit strings be directly accessible as they are with MIME types, where you can actually go in and diddle the bits as well as just know what it's to be, or both? I could imagine we could end up talking about abstract FDOs where you don't have access to the bit string, and concrete FDOs where you implement them more like MIME types, which in fact could have access to the bit string. Who's to say what's going to turn out to be the most useful in various environments? In any event, my vote is that abstract data types will be more resilient to technology change. As Bob Comm talked about, and he's a far thinker, he wants a system that is going to be usable for the next 50 to 100 years. Well, that's why he developed a handle system of PIDs that is absolutely independent of present technology, internet and the like. I mean, computer scientists are busy working on a replacement for the internet. Let's say we replace the internet with some universal network that's even better. Well, the handle data set could intersect with that just as well as it intersects with the current environment. So resilient to technology change, if you're looking for something that is going to be around for 50 to 100 years. And if you don't, if we keep replacing our stuff and can't access it anymore, that's what Peter and others have called the digital dark age. That we keep losing our stuff because we can't store it in a long-term fashion. I mean, let's face it, sheep vellum and papyrus have lasted a long time, and we're losing a lot of stuff right now in our advanced electronics because they aren't as good as paper. I think an FDO system could look just about like the web system. You'll see the only difference is I've replaced HTTP with DOIP. So my application might go to my copy of DOIP, which sends off to TCP, which finds the place I'm looking for, eventually gets to the DOIP on the computer that houses the data set, the fair digital object, which may or may not be a totally new thing. It might be a standard data set with a FDO hat on, and sends it back to me. So now, DOIP is still in development, as well as other adders are. I don't think anybody would say DOIP is a finished product. Whether it'll turn out to be this way or not, I don't know, but at least it helps me visualize what is possible. And of course, one more example of a more advanced findability application. This is the example that I'm referring to actually has been developed at the National Library of Medicine in the United States, where articles are analyzed by NLP processes to discover the key sentences in the abstracts of the articles. And the developers there say, well, there are on the average, 3 or 4 key sentences that tell you what the result that is explained in the body of the article, what the scientific result is. Now, Barron has also been a promoter of this type of technology with a better name associated with it, nanopublications. Nanopublication is a small group of triples that is a complete description of a single scientific result. Well, getting the key sentences into RDF triple format is a non-trivial job. It's taken one investigator at NLM 20 years of NLP done by, let's say, traditional methods. A second possibility, depending on whether or not you think scientists are trainable, maybe you could train the scientists to develop their own RDF triples describing what the results of their scientific article is. Perhaps more realistically, with the idea of data stewards, that perhaps one of the real goals of the data steward would be to know enough about the subject matter to be able to give an RDF treatment of the results of the program. To me, and of course, if you keep this within the semantic web framework where they have the Sparkle query language, this is a great step beyond SQL or a great step beyond web searches because it looks for connections between multiple pages. I believe that within a decade, one of the new methods of discovering scientific results is going to be mining the scientific literature, because in 2 or 3 or more articles, there are parts of what, if you put them all together, is a publishable result that people didn't really understand before. And since there are, tens of millions, maybe 50 million scientific articles out there, I certainly don't expect every scientist to read even every relevant article to what he's studying. So the idea of searching the literature, one example I'll just mention, which is pertinent to old people like me. There have been 2 scientific facts in evidence for a long time. Old men have less testosterone than young men, and old men have more sleeping problems than young men. And so a question asked by the medical community was, well, I wonder if those 2 facts are related. Well, nobody knew until Semantic Medline did one simple Sparkle query, which was able to return the fact that in one article it says that testosterone is an inhibitor of cortisol. And so if you have less testosterone, you have more cortisol. In another article, said cortisol is a known disturber of sleep. Put the 2 things together, that was sent off to the Premier Sleep Journal, which was accepted as an immediate publication, which would call for more investigation, of course, but it was something that was definitely looked for. So I think nano publications, whether we get the RDF format from NLP, from the investigators, or from their data stewards, is going to be a prominent application in the future. Repositories, digital objects are probably not going to be stored necessarily by themselves. They're going to be stored with a bunch of similar FDOs. The FDO concept is a recursive concept, so an FDO can contain other FDOs if you look at the DOA interpretation of these things. Maybe the FDOs maybe the repositories is where we certify things. Well, that's happening right now with World Data Systems in a limited number of cases. World Data Systems helps investigators certify their data sets as they put them into the data system, and that certainly could be generalized to certify for fairness, certified for all of the attributes that we consider to be important. So a certified repository would be a trusted repository. Trust, of course, is the unspoken word that none of this will work if we don't trust our data. And that is going to require work on the part of probably the data stewards and the repository people to learn how to do the certification. How do you measure fairness properly? How do you do this certification properly? This is all wonderful research to be accomplished in the future. And I'm going to run out of stuff to say here very shortly. There's a very good article. If you want to read an article that describes data science rather than a whole book, I give you a reference to a paper written several years ago called 50 Years of Data Science, where 50 years ago the statistician Tukey called for the creation of a data science profession. His statistician friends didn't listen to him then, but everybody's listening to it now. And he divided data science into 6 levels: data exploration, data representation, computing with data, data modeling, visualizations, and the science about data science. Currently, data exploration, as has been said before, and this takes about 80% of a project's time, leaving only, obviously, 20% for analysis. Well, that's inefficient and makes data sharing less useful. Wouldn't it be fun if at least with our initial explorations with these tech concepts and technology, we could reduce the data exploration population from 80% to 20%? That would be a wonderful step in the right direction. And of course, then FDOs and learning machines and so forth is highly compatible with all this. I like to think about out of the box, and I've read some recently results from from physicists who maintain that data is a physical commodity. And of course, some people have said that for the last 20 or 30 years. Is data, how do we define data? Is it ephemeral? Is it this? Is it? And this is just defining data, to say nothing of information with semantics. There's a relationship between a definition of data and our use of data that is equivalent to the old story about the steam engine and thermodynamics. Thermodynamics, the theory of heat engines, was developed after the steam engine to try and explain and understand the steam engine better. So the theory of thermodynamics owes more to the steam engine than the steam engine owes to thermodynamics. Right now, the development of data physics owes more to data technology, which gives it a reason to focus on these areas. The data physicists I've been talking about, for example, give a definition of data is any component of a physical system that is copyable. Well, I've given reference to a book you can read if you'd like to know more about that, but it turns out that being copyable is equivalent to being measurable, so it's in line with what science likes to do. And the definition of knowledge that these people come up with is knowledge is any persistent data that can transform other data without being transformed itself. Well, that's a perfect example of a computer program which has input data and output data and remains the same program to process other data. But it also encompasses DNA, which is a natural system of knowledge, according to this definition. Interestingly, this definition doesn't require the fuzzy concepts of human understandability, human semantics, and so on and so forth. So I just think it's worth thinking about in the future. The last thing I'd like to say with some gratitude is the U.S. is now playing catch-up to join the Europeans, which have been talking actively about this area for the last 5 years, and we're ready to start talking about it. We had recently had an article published in the Science magazine with a title, Playing Catch-Up in Building an Open Research Commons. Our Office of Science and Technology Policy has recently updated its requirement about ensuring free, immediate, and equitable access to federally funded research, gets rid of the one-year prohibition or the one-year incubation between publishing and availability. Our National Science and Technology Council document at the same time has published desirable characteristics of data repositories for federally funded research. My friend Bob Hainish, who is in the audience, is personally responsible for a lot of these two activities, as he has been very much at the center of waking up the sleeping giant to the importance of work on data. Another colleague of ours, Mark Mewson at Stanford, has a Nature article, which has probably already appeared. If you're a reader, you may have seen it, which simply states, without better metadata, we'll never know fair data from foul. Well, that's true. I don't think anyone would disagree with that. So think of us as coming into the game. So what do we want to do now? Well, next steps. If you were around in the early days of the internet, you know there was an annual meeting called Interop, where people who were supposed to have data that interoperated with each other got together and made it interopt. Or if they didn't, they found out why. One of the early examples of a discipline learning how to do this is the international astronomical community. Bob Hainish, who I just mentioned, was also responsible for that in his previous life. And he said that the virtual observatory, which resulted from their work, would not have been possible without astronomical interop meetings where people got together and bashed on each other until they made things work. So we'll get to the point where we want things like that. We may want things like a data IETF, which has kept the internet protocols going, or W3C, which keeps the web protocols going. In any event, we need all that, but don't let the formal specification get ahead of running code and rough consensus. One of the things that propelled the internet ahead of OSI was they never formalized anything that they didn't have two running applications for, two running implementations of. In this very building, in this very organization, the DISCO project, the Distributed System of Scientific Collections, read by my good friend Emeritus over here, is, I think, one of the premier applications that shows that this can work and can be important, as he ties together several hundred natural science collections from around Europe. I watched that with great interest. And specific applications, specific disciplines. Astronomy has already been mentioned. The application that I mentioned, that the only reason we were permitted to build the NSFNet was we said we wanted to connect 100 universities to 5 supercomputing centers. If we hadn't had that very limited goal, they wouldn't have let us do it. And then it grew like Topsy after that. Well, if all that works, then widespread adoption will come after knowledge of the usefulness and the ease of use of FDOs, and it's up to you to help us make sure that happens before 2040. Thank you very much. Thank you.
Yeah. George, thank you very much. Now I understood what you meant by abstract fair digital objects. And this was open to me. So now I would like to ask our panelists to come on stage. I will call them alphabetically. Beth Plale, you're first. Beth is at Indiana University Data Insight Center. And in the NSF, in the National Science Foundation, you worked also on open science policies. Please come on stage. Take a chair.
Thank you.
Yeah. Carole Goble, Professor of Computer Science, University of Manchester, and she is one of the authors of the original FAIR paper.
And the only woman at the meeting. Huh? Which I've never forgiven him for.
So, Carole, you should sit over there to help balance the stage here. There we go. Now we have coverage.
Raymond Drewry. I'm sorry about the pronunciation. Raymond comes from industry, from the film industry, and he is the director of MovieLabs. So we have a totally different insight. And Sharif Islam. He's data architect for Disco here at Naturalis. So we asked the panelists to create some statements, 5-minute statements, about a couple of questions concerning and into the direction of the insights George gave us. So we would like to discuss and know your ideas, or we would like to discuss some of the ideas George has presented. So one was the idea of one computer, one data set. So are there domain dependencies if we want to realize that? What practical steps are required towards this vision, at least from your personal perspective? Then we have the fair digital objects as concrete implementations or as concrete in how to call it, representations exposing also the structural details versus the abstract ones, which are more flexible. And when we are building up data infrastructures for the next decades, what is expected from the policymakers? So, and now it comes to your statements, and I don't dare to ask for an order. Who would like to start? Okay. Sorry?
Thank you. Thank you, George, for your talk. Really enjoyed it. And I also like the historical background, but I wanted to add a little bit more details to that history to give us some more context, and I think it will help us also going forward with FDO. I mean, you mentioned about DARPA and NSFNet, and I think one of the interesting things happened that between 1970s and 1990s is, of course, advent of personal computer, but also software. In particularly, commercial software really changed how we used internet and data. In particular, if we look at the history of Microsoft Excel or even Photoshop, I mean, these are amazing ways we have created our worlds in a different, even before the internet, how we deal with the data. So I think that's very important, how software sort of plays into this one computer and one network. And at the same time, from the software and the internet, we also jumped into the cloud. And this cloud idea is also very important of that whole abstraction level. And one of the interesting things happened that in the cloud environment, we forgot about the hardware. I remember when I was a student, I had to open up server boxes and put them in the server rack. Is one of the first student job I did. And we don't think about those things anymore because we think, cloud is out there somewhere. And these hardware are still there, and enormous environmental cost as well as we compute and analytic things are happening. So I think it's only important to focus on the abstraction, but also these historical details, I think, also important. And the comment about the abstract and the concrete, I think I totally agree that the abstract FDO will have definitely much higher impact than the concrete. But I think another comment I like is that we should focus on building protocols, not platforms. Beyond the software and platform, that what happened is that more and more commercial enterprises start building platforms, of course, for profitability reasons. And that's one of the disadvantage I see in some of the European projects. Is also very platform focused instead of the protocol focused. So I think to take advantage of the abstract FDO and interoperability, I think more and more we should focus on the deliverables that we produce from the European projects as more interoperability and protocols rather than platforms and portals. I think those are some of my first comments. Thank you.
Thank you very much. Beth, do you like to continue?
Good. Yeah, I agree completely with respect to the protocols and not platforms. I mean, the encapsulation and the kind of the independence that you get and interoperability to get through that, I think, is really important. So yeah. George, I feel like we're roasting you here. I have notes after notes after notes.
I look at you guys as my PhD committee for my orals.
There we go. I'll get to that. Okay. So Rainer had mentioned that I was at the National Science Foundation, and so I went in 2017. And before that, I was working in the RDA on the PID Kernel Information Working Group. I was chairing that with Tobias Weigel, who I don't think is here. He's moved on into some AI work, but I just wanted to give him a call out for the numerous contributions he made to persistent IDs while he was in the RDA. So then I had to go to NSF for 3 years, the National Science Foundation for 3 years, and I was so conflicted that I had to pull out of everything completely. And then COVID happened. So coming back here, which is absolutely wonderful to re-engage, has given me a perspective of a few years. So an observation that I actually ran on a colleague of mine, and it went completely flat, but I'm going to try it again, is this. So it dawned on me as one of the sessions I was in when we were over at the Fletcher was talking about the PID kernel information and the utilization of that PID kernel information. And the conversation, because the PID kernel information is storing a small bit of information, kind of key value pairs for those people that know what that is, and then storing that in the persistent ID record that sits somewhere else away from the data. And when one looks at that, and we were talking about what the key and the value is there, it's really a tiny bit. It's really a tiny ontology, or a tiny little PID graph that gets stored in that record. And when one looks at it that way, then its connection to a contextual, ontology-defined representation of the context makes a lot of sense. So I saw one person nod. Thank you. That's all I needed. Let me see. Okay, and then also let me call out Martin Fenner's GraphQL, or his PID graph work, which I think is important. I had a PhD student that was connecting together knowledge graphs and the PID graph and trying to utilize the PID graph as a means for deeper exploration. So I think the work he's doing in Freya there is excellent. So with respect to the FDO, or the one data, one computer, for that concept to hold, which I think is an excellent concept, what it means is there is no IP address, so that data is data addressable and not an IP address is not needed. So George, this is the roasting part of this, where you had your diagram that went from application, DOIP, TCP, through IP and back up again. That's not data addressable, that's still IP addressable. So if it's truly data addressable, there is a direct link from the request for data to the data itself, which is really what the PID provides, because the address for the PID, or information about where that data is located, is in the PID itself. So what?
This is a normal announcement.
Oh, okay.
The museum is closed.
The kids have to leave the building.
Right. So we'll give it a second. Great. Okay. So
they'll say that.
Yeah.
Please make your way to the exit on the ground floor. You are more than welcome to visit our
Oh,
floor shop until 5:30.
it's for the museum people.
Yep.
Great. All right. So anyway, so just that. So if it's truly one data, one computer, it's data addressable instead of and not needing the IP. And then that is demonstrated when one can move an FDO object or a chunk of data from, say, a DSpace instance to a file system that's served by a REST API, and there's no change in how that access is done. So in my mind, that's the criteria for the one data, one computer. So I've got other notes, but I will stop there for now. So Carole.
Thank you, Beth.
Right. So, well, how do you follow that, Beth? One of the things that I don't often promote is the fact I'm actually a professor of computer science, but I've hidden that quite well from being a research infrastructure provider and developer and working in the biosciences in Elixir. In fact, I was taught by Tom Kilburn, so I have a direct connection to the person who invented the stored program computer. And I was made professor on the basis of one of my references was from Vint Cerf. So I have some, credentials. And I also worked with Tim Berners-Lee on establishing and working on the semantic web, after the presentation, I dug out that a new form of web content that is meaningful to computers will unleash a revolution of new possibilities. And that's a quote from the paper in 2001. Well, it did, but did it produce the one data set that George suggested? No, it didn't. It didn't, because I don't think there is one data set. I think it unleashed the ability to be able to link data sets and to better describe data sets, but we still have the challenge of one computer, the network, to get access to them. But as Nicholas said, we have actually more and more rich data lakes or rich data pools that we can then cross-link. And I think what we're interested in here is a data fabric in order to be able to make those bridges, to mix my metaphors, between those different data sets, as it were. And actually, when George was speaking even more, I was thinking about, this reminds me of service-orientated architectures and all my lessons that I did and I've taught around architecture patterns. And I don't think we need more protocols. I think we need patterns. So what we should have is fair digital object patterns. And then we can have many different implementations, because what George was, if I get you right, George, you're saying in your abstract FDO is effectively, this is the pattern of how to implement this. And we know in computer science about patterns, it's abstractions. I love abstractions. I'm a workflow person. Abstractions are my business, right? But if we could develop those patterns, then we could identify the technologies that we already have. We already have HTTP. We already have linked data. We already have fair signposting. We already have RO crate. And we could say, what is the pattern using these technologies to deliver the FDO vision? And then the pattern becomes the method of adoption. Because did the semantic web succeed in its ultimate vision? Well, not really in its vision as an area of agent actionability, but it did succeed in enriching the web with semantics. Over 50% of the web is annotated with semantics, but it's not OWL ontologies, it's schema.org. It's lightweight. It's not, it's JSON LD. It's doing simple things, because in the end, the adoption path is through developers being able to adopt things to build the platforms that people will then be able to use in their science. So I think that's your adoption strategy. It's not to sort of target your funders or target policymakers. It's to target those who deliver research infrastructures for communities. My final point is that I think the role of FDO there's a great role here as a pattern factory, as a way of being able to identify how we should actually describe these FDO patterns, as it were, that are actually adoptable. And at the moment, from the discussions we heard in the last few days, even what is a type is still confused. And if I have a standard for my data because there are 1,600 standards that we know about for scientific data. Do we map them each to a type, or is it something different? So we need to settle these things, and I think we can do it through patterns. You know, I know you present a revolution, George, but I believe that, you know, revolution is only possible when it becomes inevitable. Who said that? Come on, quote. It's your PhD test.
Yep.
Do you know who said it?
No, who?
Trotsky. It didn't do him so much good, but that's what he said.
Bite your tongue.
He got his revolution.
Yeah, he also got a pickaxe in the back of the head,
true.
so yeah, whatever.
Right, so.
Thank you very much, Carole. Raymond.
So I'm a computer scientist who found his way into the film industry more or less by accident. And I come to this group because I'm also vice chair of the DOI Foundation, because MovieLabs is behind implementing a DOI for film and television content. So DOIs now identify pretty much anything you'd want to watch or wouldn't want to watch, for that matter. And the other reason is that the film industry is trying to transform itself in a data-oriented way, the same way science in general is. There's a thing called the 2030 vision. We're going to stick with 2030. About moving things to the cloud, making things data-oriented, understanding processes, and a lot of it is actually about finding patterns that people are using now and saying, that's a good pattern, let's tidy it up a bit, figure out what we can do. So listening to all the talks today, there are so many places I see parallels, and one of them is on the one computer, one data set side. The problem with the wild and wacky creative people is that they, mostly just don't care about standards. They want to say, can I watch this video clip that I've just edited? Can I do the color correction on this? If I change this line in the script, can I know how many scenes I have to reshoot? And on and on and on. So honestly, they don't care about the technology. And I think that's honestly a good thing. The technology is there only in the service of the process and products that use it. And I think it's occasionally easy for techno geeks, I'm a fully paid up techno geek, to obsess on that and forget a little bit, but what's the point? What's the point here? So we ran into this with two things. One of them was identifiers. You think, oh, identifiers, they're easy. But then you get into all these issues of what does the same mean? And you have to sort that through. And then if you have, it's the same in one context but not in another context, right? So for example, if you're looking at a rough version of an edited sequence, you might say, oh, it's the same whether it's in some iPad-compatible format or in my fancy no-loss HDR thing. And if you're the director reviewing it, that's probably true. But if you're the guy managing the Amazon cloud storage bill, it's probably not true. So sometimes they're the same, sometimes they're different. And that's something that I saw sneaking up a little bit in some of the conversations today. And if you can't say what the same means, what does one data set mean? That sort of complicates life. And the other one is, and I may get yelled at for this, but I'll say it anyway. I have come to believe that there is no difference between data and metadata. One person's data is another person's metadata, and labeling them often generates more confusion than it's worth, right? It's just a pile of bits, and you're labeling them however you want. So I see nobody's yelled at me. I'm happy. But so that's sort of my other one computer, one data set is it has to be able to understand that different people care about different parts of the data. Just the same way they care about different representations of the data. You can't just say, this is the format. You have to say, what format do you want? Yes, I can do that. No, I can't do that, but that thing over there can. So that's sort of where I've gotten to out of all this stuff.
Thank you very much. I think nobody disagrees with this statement.
Well, so I've been, how come nobody said it, even though there was sort of uneasy stirring in the audiences when the distinction was made? And,
This is exactly the point. We are coming now to the last stage of the examen. We'll ask the audience for an open discussion. Who will? Okay.
Oh, yeah. There he is.
This goes back to, even remember, Nicholas will remember, Carole, George, we wrote this exact statement on the blackboard in the Lawrence conference.
We did.
There is no difference between metadata. Technically, of course, it's data about data. But what if I am a machine? And I was the one writing it down, so I agreed with you. Not anymore. In the sense that if I am a machine or a person, and the metadata says, oh, if you click download, it's a petabyte and it will cost you 50,000 K, or the license in the metadata, as Bob Kahn says you are not allowed to see the data, I would rather see that separated from the data itself. So that there is no technical difference, it's just data about data. But the fact that we have, like we saw yesterday, a thumbnail of a painting, the actual physical thing, maybe here in Naturalis behind bulletproof glass, you have a digital image of it, and lots of metadata are associated with that. That's all data, we agree. But there is very many practical reasons to separate the metadata file from the actual object you're referring to.
So
do we agree on that or not?
I will agree with that partially, but then you'll get to say, well, then how do you decide what goes into that metadata bin?
Well, okay,
right,
but that's not a fundamental disagreement. Of course, it's a major challenge. What is metadata and what is data?
So for example,
packaging them in one object is really not the way to go.
On the licensing front, there are applications in the entertainment industry that treat licenses as data because they look at them and say, how many licenses do I have at this value, that value, the other value? And the data analysts get grumpy when you say, oh, you have to go look in the data. And they say, no, I want the license, not the metadata. Yeah, so categories are important and hard.
Okay, Paolo.
So I have a question to George and to the panel. Carole, so quoted by George, said in the year 2040 maybe we will have the EOSC. Let's think from the end. So the question is, the EOSC, as it was launched, is defined as a federation of yet existing services and infrastructures. And if we start from the end, talking about the infrastructures of the year 2040, so one computer, one data set. But the question is, do we really need all these repositories we are building up now? Do we really need all these thousands of repositories? I'm not talking about the high-performance computing, so just forget them. But the repositories, do we really need them?
Well, my answer is that distributed computing, distributed processing, distributed data will probably always be with us, and that's probably a good idea for redundancy, resilience, etc. And the internet and similar technologies makes distance less relative. So I'm guessing that at various places around the world, there will be various repositories, and that'll be good.
May I weigh into that? So people are familiar with the generalist and the specialist repositories. We were having a conversation at lunch about this, where the generalist repositories, the barriers to submitting are very low. Maybe it's the Dataset schema, it's something, or the schema.org Dataset schema. It's a very simple, but a simpler schema that one provides metadata to, where the specialist repositories tend to have specialist people that are ensuring that it's a longer curation process, but the quality of the data is higher, and it may be even in a relational database, and there's that level of quality. So my gut reaction is, why do we need a centralized solution with basically a low quality metadata schema in front of it? I don't see that as 2040. I see that as a disaster. So that's just a different perspective.
Thank you.
Hi, I would like to just agree with what you just said completely. Yeah, centralized solutions in this won't work. The question I wanted to ask is about the metadata thing. If you store data in all these different formats, you've got time series data, you've got CSV data, you've got JSON, you've got XML, all those different things. Can you truly have one data set if you've got all of these different ways of storing data in different places?
I think some of it is you have to distinguish almost the functional nature of the data. That is, what is it about? What is it telling me? And then there's a structural aspect, which is it's CSV or TSV or JSON or 80-column punch card or whatever. But it gets back to the notion of sameness again, right? Some things will only be available in one format, some will be available in multiple formats. But if I have to choose the word carefully, informational content of the two formats is the same, the only thing that cares which one is the application asking for it, I would think. So for me, that would still be one data set, but it's a smart data set. You want to give the application, and I forget who said that, but it's the applications that will drive this stuff in the long run. You want the application to get what it needs to do its job.
Mm-hmm. So the distinction between the computer and the data set gets fuzzy.
Can I also make a comment about the multiple data set piece? All the years that I've been working on this stuff for 40 years now, and the thing that always gets in the way is people. So if it was just technology, we'd be all good. But it's always a social technical situation. Mm-hmm. So the chances of you getting one data set and everybody will just manage it is really low, because people are invested in building their own data sets. They're invested in building their own repositories. They're invested in ownership around that. They're invested, the whole scientific shaboodle is built on the idea of me building something new. And so if you're going to try to move to this universality of there will be just one space, you could actually imagine, for example, in 2040, we have one common infrastructure that everybody just stores their stuff on, but there will be multiple privately tenanted databases, because that's just the way people are, and they always have been. So I think we shouldn't forget, in all of this work we're doing in fair digital objects, that there's a social piece to the technical piece. Just always think about the social, technical together, and that means working with communities in order to be able to understand what are their drivers for accepting the approaches that we're doing, and what's the vision and benefit that they're going to get out of it, as well as making it easy to actually adopt it. So, is it actually part of the value proposition for what they're trying to achieve?
And I would say, too, there's also a federal or a funder piece to that, too, where funders want to see results from research tied to a specific individual. Yes,
Yes, I wasn't going to ask this question, but then Carole made the remark about people being the problem. Yeah. And I was just thinking, so in the keynote it said that we basically now have human-style fair data, but we here at the FDO conference, we try to say we want to make machine actionable data. Whereas it occurs to me that if we were in an AI conference, we would probably say, well, just make the computer smart enough to understand human fair data. So I'm wondering, since people are the problem, should we not focus on making smarter computers, on a technology push instead of a behavioral push?
I'll let George answer that.
Can I just point out that AI gets its smartness from data?
Yeah, and I would say that our whole efforts on FDOs, however you envision them, is in fact an effort to make computers smarter. The smartness starts with the data and the computer's understanding of the data.
And the not so smartness too. You know, we could go into the whole area of bias data, bias algorithms, data leakage, and so on. So it's garbage in, garbage out, but on steroids with machine learning, and also on steroids in a black box. So I think we've got some way to go. You know, as Baron would say, the AI in the middle of FAIR stands, you know, is for AI, right? You can't do fair, AI without FAIR. Maybe you can't do FAIR without AI, I don't know. But you certainly can't do AI without FAIR.
I actually only agree to disagree with this hacking it, because I said, okay, it's good to have AI-ready data. There is not yet any AI. It's just computers.
Yeah, you need your mic to do your pitch.
We always maintain that there is no AI yet. Well, of course, some people disagree because they wanted to use it as another hype term to get money. But it is machine learning, okay, for now. And maybe if computer starts to understand, to get a grasp of near sameness, we get in the direction of intelligence. But indeed, we need to have at least the data fully AI ready if we ever want to get to AI. That's for sure.
Yeah. Okay, I think we have
If I could make one comment.
Yeah, of course.
Careful PhD student never contradicts the examining committee, so I'll be careful in that regard. But I agree that at a certain level there's no difference between data and metadata, just like at a certain level there's no difference between active data and passing data, a program or the data. I mean, look at pseudocode, which is halfway in between, for example. Right. Carole, I appreciate your comments about patterns. I stopped teaching computer science before that became the way to do it, although I did see a book that my son, who is in computer science, had that. So you actually make me go back and I will read a book on patterns, because I think that might be worth my time. And Beth, I take your point about do you need IP addresses or do you need handles? But I'm guessing that IP addresses will still, for the foreseeable future, be associated with our computers. So if you're trying to get from one computer to another, you're probably talking about an IP address. And the interaction between when do you need an IP address and when do you need the handle is something I need to learn more from you about.
So I think we have time for one last comment or question.
Okay, if you let me make a comment, I make a comment. Before I make a remark, can we get the definition of data science of George up again? This was the remark. By the time this is maybe happening or not, I wanted to say that my question to the committee would be which patterns shall we looking for? And my suggestions would be to look at semantic metrics, so to speak. So we have to look at the content of. So it's not the syntax. So it's a semiotic part, and we have to look at. Let me say loosely, how to quantify the qualitative, because we call the qualitative something which we haven't yet understood, and because we haven't understood it, we can't quantify it. That we just qualitatively talk about it. But I think so. I think that's the way we have to look for these patterns. So I think we're talking about differential differences, and. I think physics has actually started to think about these things. In the last 5 to 10 years, there have been a number of publications coming up. And if you look at your definition of data science, go through it, and these 10 things, this reads like how you do physics. Thank you.
Interesting.
Thank you very much.
Yeah, thank you. That's very interesting.
So, thank you very much. I think we should we are already a bit late, but we also started a bit late. I'm sorry for that. Thank you very much, George. Thank you very much, the panel. Ask the question to the audience. Do you think they passed with honor? Thank you very much. Yeah, that's a problem. We don't have a hat.
Uh,